In section 6.5, we're going to take a look at some applications of all of these rational functions and rational equations and inequalities that we have been working with. And we'll look at three specific types. We'll do some modeling, so some real-world situations, some variation problems, which are a very particular type of problem, and then some geometry at the end here with some similar triangles. So we're going to start with some models that we can build from the description of a problem. In our first example, we have a company that produces and sells phones, tells us the manufacturing cost is $80 per phone, with an additional daily overhead cost of $6,000. We want to find the daily cost to produce X phones per day. That I think we can do just from the description. Costs us $80 for every phone we make, and we're making X phones, so that'd be 80 times X. Plus, we have that $6,000 overhead no matter what. So there's my linear function that's just the cost of producing my X phones a day. All right, I now want to know the average manufacturing cost per phone. So this is my overall cost. I'm going to split that up amongst the X phones I make. And so my average C bar of X is my total cost, 80X plus 6,000, divided up amongst the X phones. Notice if you think about it, there's the $80 per phone, right? And there's the 6,000 divided up by the X phones. All right, the question is, how many phones should be manufactured in order for the average manufacturing cost, the C bar, to be less than $100 per phone? And it asks us to solve this one by hand. So my average manufacturing cost is supposed to be less than 100. All right, if we would like to solve that by hand, when we solved our inequalities in the last section by hand, or a couple sections ago, we always wanted to have 0 on one side. So I'm going to start with that. And then I'm going to go to my related equation. By the way, notice that the domain on this one is just X can't be 0. I'm not too worried about that because if I'm manufacturing the phones, I'm probably not making 0 phones. All right, so here comes my related equation. It's equal to 0. And I'd like to clear out the fraction, so I'm going to multiply by the only denominator in the whole thing. I'm going to multiply both sides by X. On this left side, I have to distribute the X. So when I distribute it to the fraction, the X's will divide out, and I'll just get the 80X plus 6,000. But then I have to distribute it to that negative 100, so I'm going to get negative 100X equals 0. All right, combining my like terms, I have negative 20X plus 6,000 equals 0. So 6,000 equals 20X. And if I divide both sides by 20, 600 divided by 2 would be 300 for my X value. All right, I need to test that solution. And by the way, I probably should have written this out earlier, but let me do it now. I am going to notice that my domain X can't be 0. and then I got the x equal 300. So really when I go to test, I truly should put the 0 and the 300 on my number line. All right, this is what I'm trying to test to see if it's true or false. And I'm going to choose test values of -1, +1, and 400. All right, I'm going to go ahead and put that function right there into Desmos. Can't quite get my type in there. There we go. And then -100. All right, so I'm going to make a table. And each of those x1, those test values, I would like to have Desmos plug those into my function and give me f of x1. All right, my first test value is -1. And that gives me -6020. I want it to be less than 0, and it certainly is, so that's true. Next test value is +1. Gives me 5980. That is not less than or equal to 0, so that one's false. And then my last test value, I decided to go with 400. That gives me -5, and that is less than 0. So that section is true. So there we go. First section, -6020 is less than 0, true. Next section was false, and the last section was true. Technically speaking, my answer to this inequality would be from -infinity to 0, and then from 300 to infinity. But if I think about what I'm doing here, right, my question was, how many phones should I make? Negative numbers of phones are not realistic. So what this is really telling me is I should make more than 300 phones. To be sure, my manufacturing costs are less than $100. Get that focus a little better. There we go. All right, let's try another problem. In example 2, we have a student who plans to drive home from college in Madison, Wisconsin, to Fergus Falls, Minnesota. This is going to require that they drive 204 miles in Wisconsin, which has a 65-mile-an-hour speed limit, followed by 240 miles in Minnesota, where the speed limit is 70. We are first of all supposed to find a function, t of a, that gives the driving time if the student drives a miles per hour above the speed limit. Right? So let's think first of all about time. If you think about how long it's going to take you to get somewhere, you're going to take the distance that you need to drive and divide it by your speed, right? Simple example, if you're going 60 miles and you're traveling 60 miles an hour, 60 divided by 60 would give you 1 hour that it would take. So time is distance divided by speed, or sometimes we say distance divided by rate. I'm going to use that to set up my equation here. So I'm going to start with doing distance divided by speed, but I'm only going to do it for the Wisconsin part because that's going to change in Minnesota, right? So for the Wisconsin part, the distance is 204. And if the student was abiding by the speed limit, they could go 65 miles an hour. But because they're going to speed by 8 miles an hour, I'm going to add a to that. All right. I also have to add the time that the student's going to spend driving in Minnesota. They have to go 240 miles there. Now they hit the speed limit at 70, but this says they're going to speed by 8 miles an hour. So I'm going to put their speed at 70 plus a. So there's my T of a function. Gives the time it's going to take them to drive from school to home. All right. In part B, we're asked to find T of 0 and then talk about what it means. So T of 0, if I plug a equals 0 in, that just becomes 65. And when a is 0, that denominator is just 70. And I can grab either Desmos or a calculator and just do that. Just got my calculator handy here. And I'm getting about 6.57 if we round to the nearest hundredth. All right, what does that tell us? Well, if the a value is 0, that means they're not going above the speed limit at all, right? So if they stick to the speed limit, it's going to take about 6.5 hours for them to get home from school. So at the speed limit, the trip takes 6.57 hours. All right, next we're supposed to find a so that T of a equals 6. So I want this left-hand side, the T of a to be 6. And it says we're allowed to use technology to help us with that. And once we've solved for the a, we'll talk about what it means. So I have a couple options here, right? I'm going to go ahead. I like to solve when they're equal to 0. Just makes it easier for me. I like to just be able to look for the x-intercepts. So I'm going to go ahead and subtract the 6. And then I just have to look for the zeros of the function. So since I'm allowed to use technology, let's get Desmos going here. I would like to graph 204 over 65 plus a plus 240 over 70 plus a minus 6. And I'm going to zoom out just a little bit. I think we're seeing the only x-intercept we really want there, but I just wanted to show you that even if I zoom out, I'm not really seeing much else. So about 6.4 is the a value here. All right, that's how much they're going past the speed limit, right? So if they speed by 6.5 or 6.4 miles per hour consistently, the trip can be done in 6 hours. So it's 6.4 miles per hour above the speed limit. the trip takes 6 hours. And I'm really glad we can use technology on that one because that one's a really messy equation to try to solve by hand. You know how to do it, but it's a kind of a mess. All right. Next, we're going to go to some variation, or sometimes they're called proportionality problems. And we have a few definitions for us here at the top of page 292. If y equals k of x, if y equals k times x for some constant k, then we say that y varies directly as x, or we might say y is proportional to x. And this constant k is called the variation constant, or sometimes the constant of proportionality. This direct variation varies directly. You're always going to take k and multiply it by the x. In the next one, notice here I've got k being divided by the x. When that's the case, we have what we call inverse variation. And again, k is our variation constant. So we've got the difference here between direct variation and inverse variation. All right, typically when we see a variation problem, there's going to be two essentially steps, two separate sections to solve it. We're not usually given the k value. Usually we have to solve for the k value first. And then once we do, we'll have enough information to actually answer the question that they're asking us. So let's take a look. In this first example, we're told that y varies directly as x. As soon as I see that, varies directly, I'm knowing that I'm looking at y is equal to k multiplied by x. All right, next they tell me y equals 18 when x equals 3. So what I'm going to do is plug that information into my equation, and that should allow me to solve for the k. So y is 18 equals k times x, which is 3. And you can see that k is going to be 6 in this case. So I now know that y is equal to 6x. And then the final thing that they want me to do is to find y when x equals 5. I'm now going to plug that information in. I don't know y yet, but x is 5. And so that allows me to solve and get y equal to 30. So again, you see kind of the two separate sections. Use given information to figure out the k first. And then once you know k, you can actually answer the question. All right, let's try a few more. Notice how the statement in Part B differs from the statement in Part A. Instead of y varying directly as x, now y varies directly as x squared. So I'm going to modify my variation equation just a little bit. I'm now going to say y equals k multiplied by x squared. It's still direct variation, so it's still k multiplied by, but x squared instead of x. All right, I basically have the same information to work with here. Y is equal to 18 when x is equal to 3, so let's plug that in. So I have 18 equals 9 times k. And so dividing by the 9, this time I get a k value of 2. So I now know that y is equal to 2 times x squared. And finally, I'm ready to answer the question. I can find y when x equals 5, just by plugging that 5 in for x. That'd be 2 times 25. And this time I get y equals 50. All right, I've got one more direct variation problem for us here. And again, just compare the wording to the wording on the other two that we already did. It's still y varies directly, but this time it's the cube of x. Just another way of saying x cubed. So this time my variation equation is y equals, again, k multiplied by, it's direct variation, x cubed. Plug in my given information. Y is 18 when x is 3. And I have 18 equals 27k. If I divide both sides by 27, see, was that reduced to 2/3? For my k value this time. So this time my equation becomes y equals 2/3 x cubed. All right, I now know k, so I can solve the problem. Find y when x is 5. So let's see, that would be 2/3 multiplied by 125. I can put it over 1 if I want to. So that'd be 250 over 3. And I'm just going to leave it as a fraction. You could get an approximate decimal if you wanted one. All right, so those were all direct variation problems. In D, now notice that we're going to inverse variation. Here it says D varies inversely as T. So I'm going to start with D equals, and because it's inverse variation, instead of k multiplied by, I have to do k divided by. And in this case, it's T. Direct variation, k multiplied by. Inverse variation, k divided by. All right, they tell me that D is equal to 4, or excuse me, D is equal to 5 when T is equal to 4. So let's plug that in. And just a tiny nod to what we've been doing here. I do have a fractional equation, so if I multiply both sides by 4 to clear the fraction, that allows me to solve for the k. And I can see that k is going to be 20. All right, so my variation equation is D equals, I now know that k is 20 divided by T. And I'm ready to go to the question that I really wanted to answer. Find T when D is equal to 9. So 9 for the D equals 20 over T. And notice again I've got a fractional equation, so I'm going to clear the fraction by multiplying both sides by T. I get 9t equals 20, and t would be 20/9. Once again, division wouldn't come out evenly, but you could get a decimal if you wanted to. I'm just going to leave it in the fraction form. All right, let's try another inverse one. This time, D varies inversely as t plus 3. So if I write my variation equation, D equals, varies inversely, k divided by, and then t plus 3. All right, D is 5 when t is 4. So 5 for D, 4 for T. So I have 5 equals K divided by 7. And if I just multiply both sides by the 7, I get 35 for K. All right, so my variation equation now is D equals 35 over T plus 3. And I'm now ready to find T when D equals 9. So put 9 in for the D. And again, notice I do need to clear some fractions here. The only denominator in my equation is T plus 3, so I'm just going to multiply both sides by T plus 3. Left side, I'm going to get 9T plus 27. And on the right, I just have the 35 left. So 9T is equal to 8. And T would be 8/9. So those are a few basic examples just to kind of illustrate how variation works. Direct variation, K multiplied by something. Inverse variation, K divided by something. And then just pay attention to the variables and the variations on them within the problem. All right, let's put this in context. I'm going to look at a couple of examples that are a little bit more tied into like real-world situations. Current flowing in an electrical circuit varies inversely as the resistance of that circuit. If I don't go any further, that first sentence just told me my variation equation. I'm going to have to put a couple variables around this. Current, let me call that C, varies inversely, so that's going to be K divided by, and resistance, I'm going to call that R. So there's my basic variation equation. Next, they're going to give me some information that I can plug in. We're told the current is 25 amps when the resistance is 4 ohms. So let me put that information in. 25 for current, 4 for resistance. And so if I just multiply both sides of my little equation by 4 here, I can see that K is 100. All right, so I now know that C is 100 divided by R. And I'm ready to find the current when the resistance is 5 ohms. So I'm trying to figure out C, and I know that R, the resistance, is 5. So it looks like C is 20, and my current was in amps. All right, let's give another one a try here. Car is traveling at a speed of S miles per hour, and they tell me the braking distance D varies directly as the square of the speed. So there's the description of my variation equation right there. My braking distance D varies directly, so that equals K multiplied by something, and it's the square of the speed. So speed is S, this is going to be S squared. All right, we know that if a car is traveling 60 miles an hour, the braking distance is 226.8 feet. So let's put that in. D is 226.8. That equals K times speed is 60, and that gets squared. So 226.8 equals 3,600 times K. And I can calculate my K value here. I'm getting 0.063 for K. All right, so now I have my braking distance is equal to 0.063 s squared. And I can now find the braking distance if the car is going 70 miles per hour. So find D by plugging in 70 for S. And I get 308.7. And my braking distance is in feet. And notice it makes sense, right? When they were going slower, they had a slightly shorter braking distance. We're going a little faster, so we would expect a little bit larger braking distance. All right, so that's proportion or direct and indirect variation. Our last application here in this section is a geometry one. It talks about similar triangles. So first of all, we need to talk about what does it mean for two triangles to be similar. Two triangles are similar if they've got the same angle measures. So like in these two triangles, this angle and this one, if you measured them with a protractor, would be the same. This one and this one would have to be the same. And those two would as well. Those actually look like right angles to me. I think those are probably 90-degree angles. But all three angles in one triangle have to match the three angles in the other in order to have what we call similar triangles. Once we know that two triangles are similar, there's a really nice mathematical relationship between the sides. The sides are actually proportional to one another. So it says write out at least three possible statements of proportionality. I could, for example, say that the ratio of little a to big A has to be the same as the ratio of little b to big B. Alternatively, I could say the ratio of little a to big A has to be the same as the ratio of little c to big C. Or I can say the ratio of the b's has to be equal to the ratio of the c's. Essentially, you can compare any two sides to one another, and those ratios have to be equal. All right. So my first question down here, first of all, are the triangles similar? And if so, we're going to solve for the missing side lengths in the diagram. So my first triangle down here is sides 3, 4, and 5. And it tells me that angle's 43 degrees, and this is a right angle, 90 degrees. In the larger triangle, I still have that 90-degree angle, so I already know that one pair of angles is the same. But in this one, the smaller angle, the 37 degrees, is given. So how do I know that these are actually similar triangles? I would need to show that that's a 53-degree angle there to match this one, and that that's a 37-degree angle there to match this one. The way to do that is to remember that we know something about the angles of a triangle, right? All the angles in a triangle have to add up to 180 degrees. So here I could say, if I just call this angle A for now, I could say 90 degrees for the right angle, plus 53 degrees for the one that was given, plus the A that I don't know, has to be 180. That says 143 plus A equals 180. And if I subtract 143, I can see that I do get the A value of 37 degrees. Same as this one, so we're good there. I could have done the same thing over here. Maybe if I call this B, I could have said 90 plus 37 plus B equals 180. It's 127 plus B equals 180. And if I subtract the 127, I do get B equal 53 degrees. So basically, either way, I've shown that the two triangles are similar because all three angles are the same in both triangles. All right, what I want to do next is I want to solve for the missing side lengths. I know all three lengths in the smaller triangle, but I only know the 15 in the larger one. So I'm going to call these missing sides B and little a. Actually, you know what? This is the larger triangle. Let me call them capital B and capital A, sorry. Now, in this particular case, it might be pretty obvious that to go from the small triangle to the large triangle, I've multiplied by 3. And in fact, that does work. So I can predict that this is going to be 12, and that's going to be, this is going to be 9, and that's going to be 12, right? We can predict that. But I also want to show you the math behind it, because sometimes it's not as obvious as it is in this case. So I could say 3 over A equals 5 over 15. Right? I'm saying the ratio of these two sides has to be the same as the ratio of those two sides. If I multiply both sides of that little equation by 15A, the common denominator, left-hand side, 15 times 3 is 45. And the right-hand side gives me 5A. And then I just have to divide both sides by the 5. And I do get A equal 9. Again, we kind of predicted that because we could tell the multiplier was going to be 3. But that's how you would do the math in the case where you maybe didn't see the multiplier quite so easily. Let's set up a proportion and solve for B as well. I could say 4 over B equals 5 over 15. And again, if I want to clear my fractions, I could multiply by the common denominator, 15B. So 15 times 4 is 60 equals 5B. And dividing by the 5 does give me the 12. Again, it's not surprising. We kind of predicted that. But that just kind of shows you how to set it up mathematically. All right, here's a situation where it's not as obvious. You can maybe see a little bit more why the setting up the proportion is helpful. In this case, we're told that these two isosceles triangles are similar. So I don't have to prove it. I don't have to look at the angles. I'm told that they're similar. And my goal is to find the value of x. First of all, let's review this word isosceles. Isosceles triangles are triangles with two congruent sides. So basically, because they're isosceles, I can say if that's 6.3, this must also be 6.3. And if that's 8.82, this must also be 8.82. Isosceles, two identical sides in each triangle. All right, let's set up a proportion for our similar triangles. I could say that 4 over x is equal to 6.3 over 8.82. I'm going to clear my fractions by multiplying by the common denominator. 8.82x and let's see, the x's divide out. And so I've got 8.82 times 4 is 35.28. On this side, the 8.82's divide out, and I have 6.3x. And I'll just divide both sides by the 6.3. And I get 5.6. All right, our last example here is going to look at some similar triangles that arise kind of out in the real world. Jim wants to find the height of a tree in his yard, but he has no way to reach the top to measure it. Standing in his backyard, he has his wife measure the length of his shadow, which is 10.5 feet, as well as the tree's shadow, which is 73.5 feet. If Jim is 6 feet tall, how tall is the tree? Well, let's see if we can make a picture to see where the similar triangles come in. Here's Jim, and here's Jim's shadow. So Jim is 6 feet tall, and how long was his shadow? 10.5? And if you think about what causes a shadow, essentially the shadow is just the part that's being blocked from the sun, right? So basically what we're saying here is that wherever the sun was up here, it's shining down here, and Jim's body blocked enough of the sun to create that shadow. All right, we got the tree over here, which I'm sure is significantly taller than Jim. Definitely casts a much longer shadow. We don't know how tall the tree is, so I'm just going to call it X. But we do know the shadow is 73.5 feet. And again, what caused that shadow was, we got the sun up here somewhere, right? The tree blocked that part of the sun, allowing the shadow to form. All right. How do we know these are similar triangles so that we can actually set up the proportion and solve for x? Well, I'm going to assume that Jim was standing up straight and the tree was standing up straight. So it seems like a reasonable assumption that those are both 90-degree angles. Now let's think about these angles. Why do those have to be the same? Well, if we assume that these measurements were taken at the same time, right? Basically, she measured him, she measured the tree, like right back to each other. She didn't let an hour or two pass. That means the sun really hasn't moved in the sky. And so the sun is beaming down at the same angle. So I don't know what that angle is, but I do know that these are the same. if two of the three angles are the same, the third one really has to be the same to make sure both triangles add up to 180, right? So I'd get that third one kind of for free. Those would have to be the same. So I think I do have similar triangles, convinced myself, and so I can go ahead and write that proportion. We could say 6 over x equals 10.5 over 73.5. I am going to multiply by my LCD, which would be 73.5 times x. And let's see, divide out those x's. I have 73.5 times 6, which is 441. And divide out the 73.5s. I have 10.5x. So to solve for x, I'll divide both sides by the 10.5. And I get 42. So this tree is 42 feet tall. All right, so there are a few applications of our algebraic fractions, or our rational functions, and that actually also brings us to the end of Chapter 6.